Welcome back, everyone. So today I'm going to be talking about the conversion of stilbene dibromide to diphenylacetylene. So this lab is the fourth experiment in our semester-long project. We've already purified the benzaldehyde, converted benzaldehyde to stilbene, and then from stilbene to stilbene dibromide. So now what we want to do is we want to convert our stilbene dibromide into this diphenylacetylene. And all of this can be found in Chapter 28 of your lab manuals. So the conversion of stilbene dibromide to diphenylacetylene is a very simple two-step elimination reaction. So in the very first step, we use potassium hydroxide to come and deprotonate this hydrogen, causing the first elimination, which removes this bromine. And after this reaction, we received the double bonded carbon. This will then undergo another elimination reaction, not particularly with potassium hydroxide, and I'll go a little bit more over that. But with the second elimination reaction, the same idea follows, where we'll have a very strong base that will come and remove this hydrogen and this bromine, and will form a triple bond. Something to note is we'll be using triethylene glycol, which will act as both a solvent as well as a reactant for this reaction, and you'll see why it will be the reactant a little bit later. So in the very first step, we see that we can use potassium hydroxide to cause the very first elimination. However, for the second step, this is not possible. And this is because the hydrogens on stilbene dibromide are a little bit more acidic. This is because bromine is on the same carbon, which is inductively stabilized to form the anion. Not only that, but the anion can also be stabilized by resonance by delocalizing into the benzene ring. So you can see we can move this negative charge all around the benzene ring to stabilize it. However, once we form the double bond, we lose the charge and it becomes much less acidic. This is due to the electron withdrawing bromine on the neighboring carbon. So this bromine is on the neighboring carbon, which causes less stabilization for the anion if we were to remove the hydrogen. And not only that, but now our anion exists in an sp2 bonding orbital. So before, if we remove the hydrogen, it would be in an sp3. But if we remove it now, when it has a double bond, it'll be an sp2. And so because of that, it will not be as delocalized as easily into the benzene ring. So this means resonance is not as great in the much less acidic double bonded form, intermediate. So then how do we get the second elimination to form the triple bond? So that is where our triethylene glycol, or TEG, comes from. So while potassium hydroxide may not be strong enough for the second step, using potassium hydroxide, we can actually form an even stronger base by deprotonating triethylene glycol. So how this works is the hydroxide from potassium hydroxide will come and deprotonate this hydrogen to form water, and what we're left with is a new triethylene glycol-based base that is even stronger than potassium hydroxide. This new TEG base is able to come in, rip off the hydrogen, and cause this second elimination so that we can form our diphenylacetylene. Something to note though is that even though we're using a much stronger base, this second step is still very slow, and in order for the reaction to actually occur, we might need to heat it. So that just kind of goes to show you that this step is fairly difficult to force, but we are able to do it. So just going over the step-by-steps, you can, starting with a 500 ml round bottom flask, we'll be adding our 2 grams of stilbene dibromide and 1 gram of potassium hydroxide. When you work with potassium hydroxide, you might notice that it could be a little bit sticky, and that is okay. Really, we just want to make sure that we have enough to get the whole reaction to completion, as well as adding 8 ml of triethylene glycol. So you can kind of see that this is a one-pot reaction where we just add everything into one pot and just let it go. We'll heat up the mixture for 5 minutes around 160 to 170 degrees Celsius. And then after these 5 minutes, we will cool the mixture down to room temperature. At the end of this reaction, we'll have potassium bromide as a byproduct. So we want to dissolve this by adding 40 mLs of water. And we really want to make sure that we add this water when the reaction is cool. We don't want to cause, when it's too hot and cause instant vaporization, because again, bromine is very dangerous, and we don't want it to kind of smoke up. Once we've dissolved our potassium bromide, the last thing we do is just collect via vacuum filtration, and that'll be it. We do not need to recrystallize our product. What we usually do at the end of the experiment is we weigh the amount of dry product and compare it to the amount of stilbene that we used, and we even try to determine the melting point. Once the whole lab is finished, we would then store the product in a beaker, and we would use it for the next experiment next week or whenever the next lab would be. So we recommend heating the reaction for 5 minutes at 160. It's not uncommon for the reaction to require a little bit more time than 5 minutes. So usually we recommend that when you heat up the reaction, you should heat it up for about 10 to 15, but do not let the temperature drift above 180 to 185 degrees Celsius. And this is because when the flask gets too hot, this can lead to inflammation of the triethylene glycol. So for this reaction, or for this experiment, it's important to know what your boiling points and melting points of different compounds are. So it's always good to just look up the boiling point. So for example, you should probably look up the boiling point of the triethylene glycol. So again, it's always important to maintain the temperature around 160 to 170. Try not to ever let it exceed the 185 mark. The good thing is that the boiling point of triethylene glycol is a bit high, so we don't really have to worry about our triethylene glycol boiling. However, a reflux or the boiling at the boiling point of TEG would be very dangerous, and it could even decompose our product, which is why we want to control the temperature to avoid this boiling. So the best way that you can control a boiling reaction is to really clamp the flask and then raise it and lower it onto the heating mantle when necessary. So if it gets too hot, just make sure to lift up the clamp, and if it gets too low, you drop it right back down. So once we finish the reaction, we let the flask cool down, and the reason we want it to let it cool is because we don't want to add the water when it's hot. If you add water to a hot piece of metal, like when you're boiling water, you'll see that sometimes it'll cause vaporization. And normally vaporization it can be bad, but because we're working with bromine, we definitely do not want it to vaporize and get into the air. So make sure to, whenever you're working with something hot, that you let it cool down first before you add water. So just going a little bit about the hazards that are in this lab. So again, potassium hydroxide is a strong base, and because of this, it can cause some serious damage to the skin or the eyes. Something to note is that solid potassium hydroxide can rapidly absorb moisture from the air, and this is what causes it to kind of be a little bit sticky. So that's why when you weigh potassium hydroxide, it's a good idea to weigh it quickly, because the longer you take to weigh it, the more moisture it will absorb. And just make sure to clean any surfaces that have touched the potassium hydroxide. That way we can clear out any of these hazardous spots. So not only are we working with a strong base, but we're working with an even stronger base when we have our TEG base. So again, same thing about it can causing serious skin and eye injuries, just a little bit more worse. Because this reaction has to be heated, we'll be working with very high temperatures, so be careful with what you touch. The glassware would be hot, the heating mantle would be hot, the mixture would be hot, and so you don't really want to touch this with your skin. And what's even worse is that this reaction mixture, when it's hot, is much more hazardous to the skin and to the eyes. So it's imperative that you be as careful as possible when you're working with this reaction. So just always be careful, avoid any spillage if possible, and then avoid overheating because we don't want it to boil. And again, always protect your eyes by wearing those safety goggles. Just something to note, in our lab manuals, I believe it says that 2 grams of stilbene dibromide is about 0.0006 moles, when it's actually about 0.006 moles. So now I kind of want to talk a little bit about the calculations, just give a little bit of an example. So today we're going to try to calculate the percent yield of a reaction when we're given 4 grams of stilbene dibromide, 1 gram of potassium hydroxide, and 15 mLs of triethylene glycol. After we perform this reaction, we isolate 1.5 grams of diphenylacetylene. So the first thing we need to do is find the limiting reagent of the entire reaction. So first, by doing stilbene dibromide, you take the mass of your compound and divide it by the molecular weight. So 4 grams of stilbene dibromide divided by 340. What we're left with is 0.012 moles of stilbene dibromide. For potassium hydroxide, same thing. 1 gram of potassium hydroxide divided by 56.11, and we're left with 0.018 moles of potassium hydroxide. When it comes to the triethylene glycol, because it's a liquid, we first have to convert it to its mass. So this can easily be done by multiplying the volume of our liquid, so 15 mLs of triethylene glycol, times its density, 1.1, and that gives us 16.5 grams. And now that we have the mass, we just do the same thing as in the previous steps. Take the 16.5 and divide it by 150.17, and we get 0.11 moles of triethylene glycol. So now when we compare our 3 reactants, we can see that our limiting reagent is our stilbene dibromide. So now we can continue. The next step we need to do is find the amount of moles that we form in our product. So same thing as in the previous steps. Diphenylacetylene, we know that we isolated 1.5 grams. We divide that by its molecular weight, 178.24, and we get 0.008 moles of diphenylacetylene. So now that we know the moles of our final product and the moles of our limiting reagent, all we have to do is divide the moles of what we received by what the total amount of moles should have been. So we should have gotten 0.12 moles for 100%. So it's, again, for percent yield, it's what we received over what we had, and then times 100 for the 100%. So 0.008 divided by 0.012 times 100 would give you 66.67%. And that's how you would calculate the percent yield of this reaction. So now that we've isolated our diphenylacetylene, we would try to check it using infrared spectroscopy. So looking at our spectrum, when we look at the IR spectrum, we should be looking specifically for the peak for an aromatic sp2 hybridized hydrogen stretch. So the sp2 hydrogen stretch appears above the 3000 mark. So this is our aromatic ring peak. Something very important to note is that we have a carbon-carbon triple bond, and normally these can be seen on the IR spectrum when they are polarized. When we have a carbon-carbon triple bond in the middle of our molecule, such as so, we actually do not get a signal at all. So normally there would be a very sharp peak here around the 2100 mark. However, because our triple bond is in the middle of the molecule, it is completely gone. So that's another thing that we can see. We can see that because this peak is just not in our spectrum, we can be sure that the molecule that we have is pretty likely, or fairly likely to be our diphenylacetylene. To make sure truly, we can also run an NMR. So again, the only hydrogens that appear on our compound are the ones that are on our benzene rings. So we can see that there should be 3 peaks, 1, 2, and then on the farthest edge, 3. However, because they're aromatic rings, the peaks tend to kind of mash up with each other. So you kind of get this really big mess here. But it's fine. Looking at this, we can clearly see that we only really get an area that is representative of aromatics. And because our molecule only has hydrogens on aromatics, we can be sure that this is our diphenylacetylene, or this tells us that we have purified our diphenylacetylene.